Okay, welcome back. So last week we've seen how to construct all possible representations of the single Lie group SU2, building them from irreducible representations. What we want to do today is to study a very particular representation of all possible Lie groups. So there is a particular representation that every Lie group possesses, and that is the adjoint representation. And the adjoint representation is very useful to understand the structure of general Lie groups, also to start classifying them. And it also gives rise to some more structures that one can derive in terms of this adjoint representation, which are the Cartan-Killing metric, and one can make some sense of what compactness means on the level of the Lie algebra. Okay? So to set the stage, we're going to look at a Lie group G with a Lie algebra little g. And for convenience, we're going to work in some arbitrary representation of matrices. In some, say, capital N dimensional representation. Strictly speaking, this is not necessary to work in any particular representation, but if we're dealing really with matrices, then all the operations we're going to define in a minute make sense without any doubt. Well, otherwise one have to go into some mathematical machinery. So this particular representation that we choose for G and G, it won't actually play a role in the following, just that there are such matrices that represents the elements here. Okay, so let's get into the definition of the adjoint representation of the Lie group. So definition, the adjoint representation of G, it is the n-dimensional, where n is really the dimension of the Lie group. It's the n-dimensional representation let's call it D, so it should be some mapping from the group to general linear transformations of a n-dimensional vector space. Now the nice thing about the adjoint representation is that it uses a vector space that is readily available to us, and that is the Lie algebra itself. Remember, the Lie algebra really lives on the tangent space of the Lie group, and therefore really has the same dimension as the Lie group. So these will be general linear transformations on the Lie algebra itself. So defined by the following. So for each group element G, we should get some linear transformation that linearly maps this vector space to itself, and it's given as follows. It says that d of G acting on some vector x, some generator x, does the following. And to be sure, since x and d of G, or G and x are both n-dimensional matrices, I want to avoid the confusion that this may mean some matrix multiplication. So let me introduce this notation, like quantum mechanical notation. We view this x as just parameterizing some state, and the action of the adjoint representation on the state is going to be given by taking the conjugation of this matrix X by the matrices that are associated to G and G inverse. Okay? So I claim that this really gives a new element of the Lie algebra. And clearly it's a linear mapping because x appears just once on the right hand side. So that would define a representation. And I can certainly check that it is a representation, because if I compute d of g1, d of g2 acting on x, then this is really g1, g2, x, g2 inverse, g1 inverse. But that is like conjugating with a composition of g1 and g2, right? So it satisfies the axiom that we need for a representation. So the only thing I have to convince you now is that this matrix that I write here, this capital N by capital N matrix, is really an element of the Lie algebra again. And the way to convince you of this is to note that, okay, X is not a group element, but it's close to a group element if I'm close to the identity element, if I add the identity matrix. Or in particular, if I take the exponential of X, it's going to be a group element. And I know if I conjugate a group element by another group element, that it's a group element again. So the only thing we have to do is then to take some derivative at the identity to get a matrix like this. So note that if I take g e to the power t of x, g inverse, that by the definition of a group and the fact that the exponential mapping sends generators to group elements, this is a group element again. And in particular, it's a group element that's parameterized by this real parameter t, so it gives you some trajectory in your group, e to the t x. That is the identity when I take t equal to 0. So in particular, it has a tangent vector, and this tangent vector to this curve is just x. But I can also look at the tangent vector to the parameterized curve, so this is a different curve, of course. This is the curve g e to the t x, g inverse, which will also have a tangent vector, and by construction it has to be a generator then. Right, so let's compute this tangent vector, say at t equal to 0, and lo and behold, you can perform this calculation. This is just g x, g inverse. So this vector here, which is exactly gx, g inverse, is really a tangent vector at the identity, and therefore a Lie algebra element. Okay, so this is really a well-defined representation. Now it's a representation on the level of the Lie group. It associates a linear mapping to each group element. But we've already seen 2 weeks ago that if you have a representation of a Lie group, then by taking the derivatives at the identity element, I get a representation of the Lie algebra. So let's see what the corresponding Lie algebra representation is. So what is the corresponding Lie algebra representation? Well, we know from the third lecture that in order to determine this, we have to take some parameterization of the Lie group. So let's take, just as a parameterization, the exponential of some multiple of one of the generators. And then if I take a derivative of this parameterization at t equal to 0, where it's the identity element, then I should get the Lie algebra representation. Right? Or in other words, if I expand this to say linear order in t, then the prefactor of the linear order should give my Lie algebra generator. Now, given a definition, we can work out exactly what it does. So if I let this act on our state x, then this is going to be the conjugation e to the ty x, and then the inverse. We know that the inverse of the exponential is e to the minus ty. And let's expand this to linear order in t. So I get the conjugation, so I get here identity plus ty times x. Here I have the identity minus ty, okay, plus something of order t squared. So at 0th order, I just get x back, right? That's what we expect. The representation of the identity element should just be the identity mapping. And then at linear order, I get t, I get y times x minus x times y. So that is the commutator of y and x. Let me put the ket notation around. Yeah. Plus something of order t squared. So that means that this is really the action or the representation of a Lie algebra element y on this vector space that is the Lie algebra itself. Okay, so we conclude that the adjoint action of G on itself, the adjoint representation of G on itself, is determined by just the Lie bracket, or if you like the commutator if we're working just with matrices. So this is saying that the generator y acting on another generator x is given by the generator, which is the commutator of those two. Okay. Now this sounds a bit abstract. So we said before, as in the last lecture of SU2, that to find a representation of a Lie algebra, what we really have to do is to find matrices that satisfy the structure constant commutation relations. So let us see that this definition really gives rise to explicit matrices that do this. So what are the explicit matrices, which should be n-dimensional matrices that implement the commutation relations? So what are the explicit matrices, say TA, so A equals 1 up to n, so these are explicit n by n matrices that satisfy the requirement for a representation, namely the commutator is given by the structure constants like this, question mark. But this we can determine from the abstract definition quite easily. So for this we first have to choose a basis of the Lie algebra. So suppose x a equals 1 up to n is a basis of generators, the Lie algebra. And let us introduce an inner product on the Lie algebra such that these generators are actually orthogonal to each other just for convenience. then we would like to know what, in this particular basis, the matrix elements of this representation are. So by definition, what are the matrix elements in this basis? So what are TA, so the matrix element BC of TA? Well, they're given by sandwiching these basis states X, B, and the operator corresponding to the generator XA. So it is simply given by this. Right? I want to know what the adjoint generator TA is that corresponds to the basis vector XA. And I want to know what its matrix elements are, so then I have to squash it between these states. And by plugging in the definition, or knowing that the adjoint action is just the commutator, I get that this is inner product of XB with the commutator of XA and XC. But I know that these are given by the structure constant. So this is XB, F, A, C, D, X, D. Now these are just real numbers. So and these two are orthogonal to each other. So the answer here is really F, A, C, B. Right? And in fact, in the exercises, you have checked that if you take the matrix elements of these n by n matrices TA to be defined as such in terms of the structure constants, that really these matrices satisfy the correct commutation relations. So in the exercises, you have checked that then indeed TATB is F ABCTC, and this was a consequence of the Jacobi identity. Okay. So this makes it quite a bit more explicit. But in some circumstances, it's really more useful to take this more abstract notion that any Lie algebra element acting on another Lie algebra element just gives the Lie bracket of those two. Okay. So this is definition of the joint representation. Let me now show how this canonical representation also gives rise to a canonical metric on, if you like, the Lie algebra. Okay, so we also get a canonical metric. So here is a definition. The Cartan-Killing metric, denoted by gamma AB, and given by trace of this canonical adjoint representation. So these are n by n matrices, so this makes sense, and here we have an explicit formula for them. So they're given by f, a, and then okay, I should take the indices b, c. Let's write c, d, f, b, d, c. So with the order interchanged there. So these explicit numbers, they determine a scalar product or metric on G via the following definition. So if I take so if I take two generators in this basis XA, if coefficients alpha A and beta A, then the inner product of these two generators, Cartan-Killing inner product, is going to be explicitly just alpha A gamma A B beta B. Okay. And that is always quite useful to have a well-defined inner product or scalar product on the Lie algebra. In fact, here we already used some scalar products, so here we could have insisted that this scalar product is just a canonical one that comes from the Cartan-Killing metric. Now in practice, when I give you a Lie group and I ask you to explicitly compute the Cartan-Killing metric, it can be a bit painful, because first you have to construct or determine the structure constants in the particular basis that I've given you, the basis of generators XA, and then you have to perform this computation to get this, and then do the contraction. So here's a little fact that is actually very useful in practice. So fact, one may also define a scalar product in any other representation, just the one that you happen to be working in any other representation, by setting just A, B simply to be the trace of AB. So in case that these A and B are really in the adjoint representation, so that they are little n by little n dimensional matrices, then this would be exactly the Cartan-Killing metric. But in different representation in general, this will be different numbers. But for the Lie groups that we're interested in, luckily, for the Lie groups, so let's be precise there. Luckily, if G is simple, so again I'm introducing this terminology that we have not actually defined yet, but will soon. Okay, maybe I'll just give you a definition now that you know the adjoint representation. So Lie algebra is simple if the adjoint representation is irreducible. This tells you something about the full group being irreducible, so not being able to subdivide your group into smaller Lie groups. If G is simple and the representation you're working on is irreducible, then this particular inner product you're going to define is always just a scalar multiple of the Cartan-Killing metric. Then a B is really just some constant, say C, depending on the representation you're in, times the Cartan-Killing inner product. So this depends on your representation. So as long as you're interested not in the exact number corresponding to an inner product of two generators, but are more interested in whether two generators are orthogonal to each other, or whether the norm, so the inner product of A with A, is positive, 0, or negative, one can just compute this trace in an arbitrary representation if it's irreducible. Okay, so this is just a fact that we'll actually use a couple of times in the following. So one thing one should notice here is that when we're talking about the structure constants and also about the Cartan-Killing metric, so these are tensors with some indices, they really depend on our choice of basis xa. So we would like to understand something about these objects independently of this choice of basis, because then we can start classifying what are the possible structures that this metric and the structure constants can actually take. And in order to understand this, what we should do is to understand how the structure constants and the Cartan-Killing metric actually change under a change of basis of the Lie algebra. Okay, so how do gamma AB and F ABC change under a change of basis? So let's just work this out explicitly. So what does it mean in change of basis? So it means that we can choose a different set of generators, xa prime, to be some arbitrary linear combination of your original ones. So with L, some invertible n by n matrix. Okay. So this choice of generators will lead to structure constants that are different from my original ones, but they are related in a relatively simple way. So let's see what this is. And in order to determine this, really what we have to do is take the commutator of two of our new generators, xa prime with xb prime. Okay, so let's just plug this in. So this is LAC XC, let's write XD LBD. And then we use that this is given by the structure constants. So we get that this is LAC LBD F CDE XE. That's the definition of the structure constants. And then we want to express XE again in terms of our new generators. So we have to take the inverse matrix of L. So this is LAC BD E, and then L inverse E F X prime F. Okay. So that means, let me erase this here to make some space. This means that these are the new structure constants. F, A, B, C prime. No, not C. So we took the commutator of x A prime, x B prime. So that should be a linear combination of the generators x prime again. So the index here is F. So if you're used a bit to tensors and indices, this may look a bit familiar. When you're transforming your tensor with 3 indices, you really get 3 times the linear transformation that we're doing, contracting with those indices. Okay. Okay. So what does this mean for the explicit adjoint representation, so these matrices? So this means that if you want to construct the explicit matrices in this new basis, that by definition these are given by A, C, B prime. So we can determine that from the expression here. So this is LAD, LCE, F, DEF, L inverse, FB. But then we use that this was the matrix element in my original basis, TD at position FE. So really what we have here, let's write it in matrix notation. So we have just AD, and then we have the matrix TD. The second index is matched with this L, so this is actually an L transpose, and here I get an L inverse transpose. Okay, evaluated at, let's be precise, BC. Right? So what we kind of see is that if you change this basis, then okay, so one thing that happens is that the different generators of your adjoint representation get mixed a bit by this LAD, but also the actual matrices, they get conjugated by this linear transformation L. So now if we plug this into the definition of the Cartan-Killing metric, what we find is that gamma AB prime, so that is the trace of TA prime TB prime. So that gives me a LAC LBD of the trace of this part. So I get an L inverse transpose TC L transpose, and then for the other T prime B, I again get an L inverse transpose TD L transpose. And now we observe that really this conjugation, it drops out of the trace, right? So this term cancels that one, and by the cyclicity of the trace, this one is going to cancel that one. So we're really left with here just the Cartan-Killing metric of the original basis. So this is LAC LBD gamma CD. So we see that this 2 tensor it's a symmetric two tensor. It transforms under a change of basis by just this standard contraction of the linear transformation with the two indices of this metric. And this is exactly what you're used to, say in general relativity. If you have a metric, then it also transforms exactly in this way. So it transforms as a metric like in GR. Now that is useful because now you can actually use your intuition that you have, say from general relativity, on how restrictive, what the possible forms are that the Cartan-Killing metric can take. Because if you remember, in general relativity you have your arbitrary space-time metric, but you can always, by choosing your coordinates properly, locally bring it to a very special form, which is just the Minkowski metric. So the Minkowski metric, it has, so what does it look like again? It has minus ones and ones on the diagonal. So remember, you cannot change coordinates such that you just have ones on the diagonal or minus ones, because this minus one really tells you something about the time direction in your manifold, in your space-time, being special. It comes with a different sign. So quite generally, if you have a symmetric matrix, gamma CD, one can always choose a linear transformation L such that your matrix becomes diagonal, and you can put ones on the diagonal, or zeros, or minus ones. You cannot change the signature of the values on the diagonal. Okay, so I can choose a basis such that gamma AB looks like this. So I have minus ones, then I have perhaps several ones and zeros. And this is the best thing you can do, the most restricted thing. So this you could compute for every for any kind of Lie group that I hand you, and in particular you can then extract what is the number of minus ones, the number of ones, and the number of zeros. And they have a clear interpretation. So the ones correspond to compact generators in your Lie group. So what do I mean by a compact generator? A compact generator is really a generator that if you would, so here's the identity element, and you would follow the exponential map of such a generator, well, it would have compact trajectories. This is like this is a typical compact direction. For instance, if you look in the Lorentz group, then rotations are compact, because if you rotate by 2 pi, you're back at the identity. The ones correspond to non-compact generators. So an example of this in the Lorentz group would be the boosts, and they correspond to trajectories that really take you in some non-compact direction of your Lie group G. So these are non-compact. And then there are the zeros, which are called nilpotent, and they can be either compact or non-compact. Nilpotent generators. And this classification of generators is quite useful, because it tells you something about the compactness of the group. So now we're getting to the final point of this video. So let me put that here. Definition: a Lie algebra is compact if the Cartan-Killing metric is negative definite. So meaning that if you diagonalize it, you only have, well, in this particular diagonalization, you just have -1s on the diagonal. And these will be the Lie algebras that we're gonna focus on in the remainder of the course. And it includes all the special unitary groups and special orthogonal groups that we introduced a couple of lectures ago. So here's a quick remark here that is important to keep in mind. The fact that the Lie algebra is compact, Lie algebra is compact, that certainly implies that the corresponding Lie group is compact. So remember that I said that the Lie group is compact if you can write it in terms of matrices whose matrix elements are all bounded. So this is in particular a Lie group that is not compact because it has these infinite directions, but if you get some closed manifold, then it is. But this is, the reverse is not true. So it is possible. So when a Lie group is compact, that implies that the Lie algebra, that the Cartan-Killing metric is semi-negative definite. So which is saying that we can also have zeros in the diagonal. As I said, nilpotent generators, they can either be compact or non-compact. You can't judge just by looking at the Lie algebra structure. So whenever we're going to be talking about compact Lie algebras in the following, we're always talking about this notion of compact. So the Lie algebra being compact, meaning that the Cartan-Killing metric has -1s on the diagonal. So an example of a Lie algebra that, or a Lie group that is compact is U1. So these are just complex numbers of modulus 1. But the Lie algebra is trivial. So in particular, it only has a 0 in the diagonal. So it's actually nilpotent. So U1 is compact, but its Lie algebra that we would denote by small u1 is not compact. So this is just a side remark. Okay. Okay, so let me write one more thing. However, a simple compact Lie algebra on one side is the same as a simple compact Lie group. So that's also why this example fails. U1 is not a simple Lie group. But as soon as we restrict to simple Lie algebras and Lie groups, which we'll do in the following, then compactness of the Lie algebra and the Lie group is actually the same thing. Final remark. In a basis of a compact Lie algebra where gamma AB just has -1s on the diagonal, it can be shown. Okay, so and this is done in the lecture notes. So this is paragraph 5.2 at the end of it. that the structure constants in this basis F, A, B, C are completely antisymmetric. So by construction, the structure constants are antisymmetric in the first two indices, but in this particular basis, it's antisymmetric in all pairs of indices. And this is the convention that is usually used in quantum field theory. Convention used in particle physics. So we're always in this basis, so one is always assuming that the structure constants are completely antisymmetric. But this is really a particular choice of basis that one is doing. Okay, so that's the end of this first half of this lecture. In the second half, we're going to look at another consequence of having this adjoint representation and the Cartan-Killing metric, which is the nice notion of a Casimir operator.